Swayam Prabha. Digital India. Educated India.
Good afternoon, welcome back. I'm glad you're back. I'm glad you decided this was worth your while to come back to class. So we'll talk about still the motivation for doing all of the work that we're doing. And for today's session, we'll talk about energy and carbon dioxide. Why do we relate carbon dioxide to or the energy sources, the production and the consumption of energy to greenhouse gas emissions, and what are the main sources? I had a question from one of you requesting for data links. I think I have something in the slides in the second part. We also have PDF versions of all the slides for today and yesterday. They are with Prerna, and they will be shared. Yeah, so they will be shared soon. So you should have access to everything. Has been shared. Okay, good. You're faster than the police allows. Okay, so we'll talk about the Keeling curve. We touched on it briefly. We'll listen to the talk from one of my PhD students, Dorothy Kanini Manzia, and she talks about her motivation and the relationship what she sees between where she comes from, a small village south of Nairobi in Kenya, and the work that she's doing and the motivations for doing it. And then we'll look at the sources of energy production. We'll look to see why do we relate greenhouse gases to energy, what are the energy sources, what are the generations of greenhouse gases for each type of energy. We'll look at the energy mix, and we'll look at the, I think in tomorrow's talk, we'll look specifically at some data from India, where we stand, what are the major sources of energy, what are the emissions, where are we getting emissions from, and how do we know what is there. And then we'll look a little bit today at how do we come up with a value of 1.5 degrees centigrade or 2 degrees centigrade above gas. What is the reasoning behind that? Why do we say we only have 20 more years to burn fossil fuels and then we're done, or 50 more years, and what do we base that on? So we'll look at some of those data, some of those calculations. In the topics that we'll address today, we will look at extreme heat. I think there are two videos that you should watch. One is a very nice one. It is from COP29, trying to explain what are the terminologies we typically use. So if you're reading any of the climate change papers and articles, there are certain jargon that we use, words that have a meaning, but no one explains them. So if you're really struggling with that, I would watch this. These are all 10 minutes long videos, 10, 15 minutes max. I think maybe one or two might go up to 20 minutes. So at your own time, watch this one. The second one is Life at 50 degrees centigrade. And this is a very new one. This is from a compilation of what it meant with extreme heat. And I found this to be really interesting because it allowed, we also looked yesterday at balancing the budgets, and there are slides that were handed out yesterday. We didn't go through them, on calculating temperatures, on doing the thermodynamic balance of incoming and outgoing heat, and calculating the temperature change that you can expect from that imbalance. So we'll not talk about that today. We will look today at the greenhouse gases. Keeling curve is something that you should be familiar with. The Keeling curve is this one. I'm told I should use this one and not point to the screen because online audience cannot see that. So I apologize for that. This is the red one is the Keeling curve. It's the level of carbon dioxide in the atmosphere. If you check over here, we started at 320. We are now at 420 within 60 years. Within 60 years, we have raised the carbon dioxide levels in the atmosphere by about 100 ppm, and that's a lot. Together with that, we have a temperature increase out here, and we looked at these data yesterday. Right? So if you overlay one on top of the other, this is what you get. Here's the Keeling curve. This is the temperature anomaly. Now, this is nothing new. It has happened in the past. So these are 800,000 years of data on temperature or on carbon dioxide concentrations. Some of these are from ice core data, from trapped water, trapped air in ice that we can study and look at what the concentrations are. So we see that there has been fluctuations like this. This is the highest previous levels that we've had. That's 300 parts per million. Right? And we seem to be going up and down. That seems to be the normal cycle. This is our cycle, and here we are at 320. That's when we started measuring. That's when the Keeling curve starts. And if you take that in the same time scale, this is where we are today. That's the difference. It did not come down again as we have observed in the past, as the geologic times records have shown us, but we continued onwards, and this is the part that is modern data, that is today's data, that allows us to say we are headed for a problem, because if we do not clean this up, this will not be reversible. So we are looking not just at recent data that we can measure, but ancient data and much more Holocene data that we can actually measure through various other trapped air measurements. So we then talked about the changes due to various forcings. We have different models that give us certain amount of warming with time up to 2100, and depending on what models we run, we have either 5 degrees centigrade warming, or we can go down to 1.5, which is what, if you remember, in 2015, this was the Paris Agreement, 1.5 degrees above gassed, 1.5 degrees temperature anomaly above global average surface temperatures. So that's where we are. This was a very ambitious target. We agree that we are not going to reach that. There is not a possibility, there is no scope, and there is no thrust by governments, by nations, by people, by all of us in the collective effort. There is no impetus. Nothing is giving us that drive to say we have to stay at 1.5 degrees or below. So we're not going to reach that. Okay, so we leave these two models aside. The next one is we are going to be around 2.5 degrees, 2 degrees, 2.5 degrees by 2100. 2050 is right here. So this is what we are talking about. When nations say we will be 50% less renewables in 2030, net zero by 2050, they're looking at these models and they're calculating. and they're saying this is what we can realistically reach. So if we take this one here, 2050, we say 2 degrees is what we are today sort of saying this is where we will be, 2 degrees above the normal average temperatures. That brings us to the climate model of 2-4.5. Okay. So what does that mean? What is this sort of calculation that we do? These are the different models. What we're looking at is a temperature increase. We're calculating the temperature increase from the greenhouse gas cover that we have based on the cumulative emissions that we are driving, right? So here is 3000. So today we are somewhere here, 2020, where are we, 2020? Somewhere out here. So this is what we have. Today we are at 1.2. I think you saw the slides yesterday. We came up with about 1.2 degrees above cast. So amongst friends, we can take about 1 degree centigrade above cast, and we say the level we have reached is 2,200 gigatons of carbon dioxide, right? And now we follow these ones through and say we do not want to reach more than 2.5, so we really don't want to get here. We want to stay at 2 degrees centigrade. So we follow this line here and we say by 2050 or whichever time we want to be, let's say we want to be out here. So we are in this place here. So that's 2 degrees coming in. And so we have 3,700 gigatons of carbon left. 2,200 and 3,700. So 3,700 minus 2,200. That's the amount of carbon dioxide that's left in our budget, working backwards from the temperature we allow to be increased. Are you with me? Kind of, sort of? Okay, good. Yes. Okay. So really. Yeah. Yes.
It's a problem for us, right?
It still will be a problem for us. Yes.
Yeah.
It is not a trivial thing to say, yes, we'll have 2 degrees increase, will allow it to happen. We have no choice. You see, that's the dilemma. So what we're really doing is to say, where do we absolutely have to make a change because we cannot sustain life beyond that? So that's really the argument, not so much as being a choice, but as being a necessity to be able to do that. You're right, it's not a choice. And I'm sorry if I presented it as a choice. It is not an easy thing because this is where we are, right? So that's the level we've already put in the atmosphere. If we don't want anything, we should be out here. So we are calculating, in a way, what is it above this norm? If we don't want anything if we want to be at gas, we need to remove all of this out of the atmosphere. We're not going to be able to do that. So that's a given. So now we're looking at saying, okay, we already are at 1 degree centigrade above gas, and we will allow 1 more degree above it. How much do we have of emissions that we can put out in the atmosphere as an entire globe, all the nations, everyone together, right? So these are cumulative amounts of emission in the atmosphere since 1850. So when we talk about being able to, I'm sure you've heard people talk about tipping points, tipping point in climate. Tipping point in climate is we've put so much emissions out in the atmosphere, we really cannot bring the climate back in. There's nothing that we do because we've heated the oceans so much. It's going to store heat for a long time. Where there is no way we can control anything. It's beyond our control. Everything we do is going to not make much of a difference. We have tipped the climate over to be constantly warming. That's where we are not there yet, but we're close. And that's what the climate scientists are sort of calculating to see how much time do we have before we cannot make anything change. I have to remember I'm keeping track of where I am in the slide so that I'm not going too far ahead. The same thing, same information as a table. This is approximate global warming relative to 1850 to 1900. We had this discussion yesterday with why take 1950 to 1980, right? It's already in the industrialized zone. So this is from the IPCC report. I apologize for that. I've moved it around. So this is the IPCC report AR5 that came out in 2013. By the way, there is a newer report that came out in 2023. That's the AR6. So if you're interested, you should compare data from AR5 with AR6. AR6 shows you a much worse picture. But we stay with this one today. So this is relative to 1850 to 1900 and 1.5 degrees centigrade. So we say additional global warming from 2010 to 2019 until the temperatures reached. We will reach there very quickly. It's not going to happen soon. What is the likelihood and how much carbon dioxide, how equivalent do we have that we can emit before this is no longer reachable? So we know this is no longer reachable. So we go another one here, or we go this one here, right? This is a decision that we can make. We can make a decision. Let's say we go with 1.7 degrees centigrade, that we allow the temperature to change above the baseline temperature. If we do that and we want it to be a likelihood of 17%, we say 17% likelihood we'll meet that, then we'll say we have 1450 gigatons of carbon dioxide left in our budget that we can burn. If we want much more certainty, we really want to nail this target, we really want to reach it, then we have only 550 gigatons of carbon left in our budget. Okay, so these numbers are what governments fight about, because this is really where our economy will come from, right? The economy is, I think you heard Professor Sangwai talk about the economy of a nation, the wealth of a nation, the emissions of a nation, the energy consumption of the nation. All of those are tied together. So if we are saying, let's say we are the United Nations, we're sitting together, we are different nations, we're all sitting together, and we have come to an agreement, we will allow, we can deal with, let's keep it realistic, 50% likelihood that we should keep the temperature below at 1.7 degrees above gas. And so we have 850 gigatons of carbon dioxide to put out in the atmosphere. All of you represent different nations. How are you going to divide this into saying, okay, USA can put in 50 gigatons because it's the big gorilla in the room. And let's say France, they complain a lot. They say, we'll take another 20. And then other countries come in, they take away 20, someone takes away 50 and so on. And now you come to smaller nations, right? You come to Tuvalu, you come to Tonga, you come to Papua New Guinea, you come to poorer nations. They don't have much bargaining power. And so the part that we worry about is to say that this thing will be occupied by countries that are already rich, that are already consuming a lot of energy, and with that putting out a lot of emissions already. So the challenge that COP29 was talking about and fighting about and arguing about, and many nations stepped away and said, we're not going to be part of this discussion because it's fundamentally unfair. And that is to say, how do you divide up that 850 gigatons of carbon dioxide in a manner that allows every nation to still grow, that allows every nation to still care for its citizens and give them a decent way of living? What are the sources now? Right? If we are going to cut, let's say we need to reduce our emissions, we have a level of 1450 gigatons of carbon dioxide that are put out in the atmosphere, and we want to reduce it down to 850. We need to know where they're coming from. And that's dependent on each country's consumption levels, emissions levels, and what are the generations. So what are the greenhouse gases being generated from? So we have, these are US greenhouse gases. The links to all of these data are over here, and they're on the slides. I don't know who asked the question, but all of these things are available. This is I think this is a graph. I don't know if I made it or I got it plotted on the website. It doesn't make a difference. You can get the plot and you can get the data that were used to make the plot as well. So this is for the US. The status is 2019. It's not new. This is from the Environmental Protection Agency, but you can get similar data from NASA or climate.gov. And that's for the US. You can get similar information from Europe, and there are data like this that are available for the entire globe from Our World in Data. There's a website, and then we'll come to that website as well. So this is the greenhouse gas compositions that we have in the US in 2019. A majority of it, 80% carbon dioxide, 10% methane, nitrous oxide, and fluorinated gases. Those are the major components. If you look at the sources, you have transportation, 35%, electricity, 31%, industrial use, residential, and other uses. So that's what is generating. This is the source of carbon dioxide or carbon dioxide equivalent emissions. This is the composition, average composition of the emissions. Right? We can do this year after year. You get these data. So these data are available for most countries. Here, I think you can get temperature data from Mausam Bhavan. You can get the Petroleum Ministry has energy data. So you would need to piece it together more, but all of the data are available, especially if you belong to a research organization in India. Universities have access to the data, you just need to ask them for it. Sometimes it takes a while. Sometimes it takes a while for people to release the data, but those data are available. Those data have been collected. So if we are looking at emissions, these are historical greenhouse gas emissions. We have United States on the top. We have China out here, European Union, Russia, Brazil, and so on. So these are historical emissions by these major or major contributors to greenhouse gases. My question to you is this a fair way to depict? This is data, right? The data, not exactly, okay? Right. So if we look at it by per capita, right? Normalize it by population, that information comes out to be very different. That's what it looks like, historical emissions per person. US, Canada, Russia, EU. And EU, that's UK. So if you add all of that to say Europe rather than EU, that gets to be very large, right? So that's another way to look at it. What would be yet another way to look at this? Area, right? Area. So you can divide this up by area. How much are we generating based on the area that we occupy? This will look very different. What else can we use? Industrial production, right? Generation, because a lot of things. So China argues, wait a minute, those emissions are not for us. You guys are buying everything, so we are selling this. Right, those are oil production. So if you look at Qatar, they say, wait a minute, it's not for us. You guys are buying our oil. That's why we have this. Saudi Arabia, same thing, right? What else can we do? Based on consumption, but that would be like per person. There's one more factor. GDP. Yes, you can base this on GDP. The whole picture looks very, very different. So when we are trying to allocate 850 gigatons of carbon dioxide left in our budget, that's what we are fighting about. When we have conference of parties of all nations, one person says we should do it per GDP, the other one says by area, someone else says, wait a minute, no, this should be historic emissions, everything that you've generated over time, not today's emissions, but historic emissions. And that becomes a very difficult thing to do because everyone obviously tries to do things the way that makes them look good. Right. So that's the argument. There is a very nice, in the links that you have, there is a very nice video by a young lady, Mutisu, who says, all the developed nations have burnt all the forests. And this was, if you remember, the Prime Minister from Indonesia, I think many years ago, 20, 30 years ago, Mahathir, who argued, said, you guys have burnt all your forests and you have running water, you have electricity and everything. And now you're coming to us to say, hey, you can't cut down your forest because these are the lungs of the globe. Doesn't work that way, right? At the same time, it doesn't matter if others have polluted more, we still all need to curb, right? So there has to be some middle ground. It doesn't help to say, okay, you've you've driven this far down the hill and I'll drive the rest of the way down the hill. We are trying to find our way back up to the top of the hill. So this is a difficult argument to try and win, because there is really no winning this argument. We have to reconcile. We cannot fight history. It is what it is. Right? At some point, we have to agree and say, okay, yes, you guys were really bad. You colonized, you did this, you robbed and you did this. You burnt everything and you put all these emissions out in the atmosphere and we're dealing with it now, but we still have to deal with it. So we can be grown-ups and say, okay, you know what? You will pay for everything we have to do. Right? That's the impasse that we are at today, where COP29, I don't know how many nations walked out of the agreement to say, yes, we have an agreement in place to pay poorer nations $330 billion per year to take care of emissions. Doesn't even come close to what is needed. Yeah, no, that's not telling the full picture. There is fluctuations, and it seems that way, no? It seems that way, but this is not correct, because if you look at yes, it might be, it's a slight decrease, but that's the emissions control that US has been following. So it's possible that is real. It's peaked around 2015, yes, but this here says it peaked somewhere around 2010, 2007. So, yes, but this is too early for CCUS, right? So CCUS would have come somewhere here. So I don't know what the cause is for that one dip. It could be slight changes in either an economic downturn, which it was a time of economic downturn that time. So it could be that thing, and then together enhancing somewhere out here 2010, 2012, when the CCUS policies came about. So it could be a combination of that. China's been in the news a lot in the past few months, and there's been a big complaint that China is emitting more than US or more than EU. But China is looking at this and saying, wait, we are emitting more than you only today. You guys have been emitting all the way throughout. So there are multiple ways to dice the data. There are multiple ways to present the data and put it in such a way that allows us to look better. Which comes back to someone made a comment saying, are we really doing something, or is this just optics? And from all of the rhetoric, it seems like oftentimes it is more optics than anything else. And that's the part which is troubling. Again, Carbon Brief, IEA, excellent sources for data. So this is from the New York Times a few days ago. They've recreated the graph getting data from, I think Jones et al. Were the ones who compiled everything, but they got the data from Carbon Brief and IEA. So it allows everyone to create their own plots. The part that really struck me was a talk by Dorothy. This is a student from Kenya. She is doing her PhD on CCS in my group. This is on YouTube. It's a TED-like talk. And we have the Global Energy Futures program. And that's Dorothy talking about the motivations for her work. I don't know.
Today, I want to talk to you about something that holds incredible potential in our fight against climate change: carbon capture and storage, or simply CCS. CCS is a technology that has the power to transform our world and protect it from devastating impacts of climate change. I moved here to Colorado 2 years ago from Kenya. This is my village in eastern Kenya, where I grew up. It's beautiful, lush, and green, far from factories that emit carbon dioxide. So you might think the atmosphere here is clean and pollution-free. But if you look at about 200 miles away, you find Nairobi, a city with a lot of factories and industries emitting carbon dioxide into the atmosphere. We all share the same atmosphere. We breathe the same air. It doesn't matter where you live. The CO2 in the air will reach you. Take, for example, the beautiful Mauna Loa, Hawaii. Even though it's thousands of miles away from the major polluters and 11,000 feet above the sea level, scientists have tracked rising CO2 levels there. From my village to Mauna Loa, we discover a fundamental truth. Regardless of where emissions originate, whether nearby or far, they inevitably find their way into our shared atmosphere. But we can significantly reduce our emissions with CCS, where we can mitigate the effects of climate change, and where we can slow down the rising temperatures and protect our environment for generations to come. So what is CCS? Basically, you drill a well down a couple of thousand feet down into the Earth's surface. You pump the CO2 in the rock formations down below, close off the well, and it will stay underground, trapped within the tiny pores of the rock.
So what Dorothy was talking about was really this curve here. That's the Keeling curve, measured on Mauna Loa, thousands of miles away from any industrial zone. And so the challenges that we are facing is an equitable way to distribute emissions, an equitable way to distribute and allocate emissions, almost like rationing out, right? You have a ration of 850 gigatons of carbon dioxide that's left to emit, and in that we have to make sure that we are meeting our country goals. How are we going to do that? That becomes the challenge, and that's pretty much what the challenge that I proposed to you was. If you are part of a state, you're an elected official, and you're told the entire world has 850 gigatons of carbon dioxide left in the budget, you need to come up with a plan to reduce 10% of your budget. How are you going to do that? Do you think that is fair, given what your economy is, given what your consumption is, given the GDP of your state?